Hello, hello.
Hello.
Yeah, I was in a meeting and it ran over, so.
That's not a problem. That always seems to be the case anyway with meetings.
Yeah, but online it's even worse.
Oh, yeah.
Oh, hi, Ben.
Yeah, I haven't edited the lecture 2, so I'll crop that a little bit as soon as I figure out how to crop. I'll crop this out as well.
Okay. I have to leave in about 25 minutes because I'm on another meeting.
That's how bad it's all going. It's about a 45-minute lecture. I try to keep it to about 45 minutes. Then,
okay. Yeah, I will just watch it then later on. Okay.
All right. I'm about to kick off, I think. It started. Right. Let's see if I can. Works. Okay. So galaxy morphology, the appearance of galaxies. Lecture 3, the Galaxy Zoo, or citizen science. And so instead of relying on specialists, we're now going to go to the crowd. So crowd classification. We talked about visual morphology as it has been done in galaxy-wide profiles, so Circic profiles, vocular profiles, and exponential profiles. And then we talked about sub-galaxy scale morphological phenomena. So anything that's basically within the galaxies, but about a kiloparsec or more in size. And yet everything that we've done so far was based on the inspection of photographic plates effectively. Today we'll talk about crowd classification. Next week I'll talk about morphometrics, which is another way to turn all this stuff into numbers. And then after that, low surface brightness features, and then morphological evolution in the future using machine learning. So far, we've relied on things like this expert classification, where we have an expert like the Vocular up there or Hubble, and they're basically assigning, they've got a sketch, they've got a classification system, and they're sort of assigning these various we have to go hit escape and admit somebody. There we go, admit. Fantastic. Okay, hello, welcome. I'll just keep going. And so what we've been doing so far was just relying on a single person classifying galaxies and hoping that they're know what they're doing. So, for example, we had the Hubble classification scheme, so the Hubble tuning fork. And so if he said it was an E3, it was an E3 galaxy. If he said it was an SA, it was an SA galaxy. So that's what we've been relying on. Now I'd like to keep going. Hello? Oof, okay. And so we want to update this, right? So this is a updated version using the Sloan Digital Sky Survey from the same Hubble tuning fork. The credit goes to Karen Masters, and so you can see that yes, there's also color information in these classifications, right? So elliptical galaxies are red, and spiral galaxies have a blue disk typically, but some of them are a little redder, and the bar is typically red. So we've got red and dead, massive N clusters, elliptical galaxies, and we've got, okay. Escape, admit somebody, and also my computer's having some issues. So that's always good. Okay, good. All right, I'll keep going. Forging ahead. So we have the Hubble tuning fork, and we have this wealth of wealth of the digital library of the night sky. So we have color pictures now rather than single color photometric plates, and they're all digital. And so the Galaxy Zoo is sort of the next question is like, let's go and classify these based on their appearance in the new digital era, so to speak. And but this is the sort of what we were left with before the citizen science really kicked off. The The elliptical galaxies were massive. They were red and dead, meaning that there was no new star formation, and all the star formation was happening in disk galaxies, which were less massive, and they were not in clusters. So this is what we knew when we got started. And so if you put that on a color magnitude diagram, you have smaller and dimmer on one side, you have brighter and bigger on the other side. So you can have mass or the equivalent luminosity on the x-axis, and then put color on the y-axis with bluer and redder. And so you've got a blue cloud, that's all spiral galaxies, and you've got a red sequence, and that's all ellipticals. And that's how we thought of galaxies as a whole. And so that's what we got from the experts so far. Now, the thing is that those are sort of the 90% truths. And then they're in the middle was something like green galaxies, which are very, very sparse. So there was nothing there. This is sort of what it looks like in real life. And then the idea was to go like, well, let's go out and classify these galaxies. But now, how to look at these millions of galaxies in the Sloan Digital Sky Survey. Famously, this was a British project, so it started in a pub. And essentially, this was a grad student was asked, hey, could you go and classify the Sloan galaxies, but using the Hubble tuning fork, for example. And he got started. And if he had worked flat out, he got 50,000 of them done. And so if you get 50,000 done in a week, that means 1 million galaxies is going to take you way longer than a PhD project. So you need a way to speed this up. So how does this work? So you ask multiple people to classify the same galaxies. That was from Kids in the Hall, and I'm aware that nobody else has actually seen Kids in the Hall, but I don't care. And so you'd ask multiple people all to look at the same galaxy and give their opinion, and then just ask many people to go look at all of them, all the objects that you're looking at. So these are all the Hubble pictures. And so you train people to go, oh, that's an edge-on galaxy. Oh, that's an elliptical galaxy. It doesn't take that much work, and it's actually fun to do, but it's not fun to do when you have 50,000 a week to do. And so if you do that and you start asking people about, is this a spiral galaxy? Yes, no. Is this an elliptical galaxy? Yes, no. You start noticing that the color and the shape aren't as strictly connected as you thought they were. There are spirals that are just as red as the typical elliptical galaxy, and there are ellipticals that are blue, that are star forming. So that was the first part of this that was surprising. There's substantial minority reports, so to speak, like there's these 10% of these populations that are not following what everybody knows part about galaxies. And so the fun thing was that this started off as a crowdsource. So basically it's a website. This is just when smartphones were starting to get introduced. But first it was just a website, and Brian May got involved and he tweeted about it. And then, all his followers started doing this as well. And so this was a massive hit for people to just go and look and help with classifying galaxies. Is this an elliptical? Is it a spiral? Or is it none of these things? And so a well-designed so you classify by crowd consensus. If everybody agrees or a majority agrees that this is a spiral galaxy, then it's definitely a spiral galaxy. So we don't rely on a single expert anymore. We asked a bunch of people for each galaxy. That was the life of Brian. Again, something that no student has seen because it came out 40 years before they were born, but that's no matter. And so we found things like red spirals. We found things like blue ellipticals. We found things like very, very rare objects. And so the good news was that because you now have multiple classifications, hundreds per source, really, you can start saying you can assign a probability that this is true rather than saying it's either yes or no. You can actually say, here's my probability function, here's my voting function for this particular object. And so the Galaxy Zoo 2 happened. So there was another iteration of this. We take 250,000 galaxies and we just ask detailed questions about the nearest galaxies. So the things that you can see more detail. And so the kind of stuff that we talked about last week, anything like bulges, bars, ANSI, and how many spiral arms do you see? How tightly are they wound? Do you see anything else? And so this became more and more popular and actually ran, you can see this runs for about a year, and then suddenly you have all of those things classified into extreme detail. So this is sort of what this looks like. And this is, as you can see, this is starting to look like buttons on an app. So you start at the top. Is this smooth? Is this featured? Is it neither? Is it a star or some artifact in the images? And then it goes, could this be edge on? Could this? And so you are left through this, go through this flow diagram. But essentially, this is just you looking at a picture and hitting a button. And so this is something that you can just, I don't know, do while waiting on the bus. And it doesn't mean that everybody classified all of the 250,000 galaxies. Quite the opposite. Everybody classified how many they felt like it. And then the aggregate can be used in order to classify each individual object. So for example, you start tossing out people who basically hit, who've, left the phone in their pocket and then just hit star artifact for every object, for example, that stands out. So that gets nixed. There is in fact somebody who went through all of Galaxy Zoo twice. And so that person just really liked it and classified all the galaxies twice. So they kind of had to downweigh that guy a little bit. And so this is data and it has to be edited as, or it has to be calibrated approximately or appropriately. But I do want you to note that there's all these different questions that are being asked about the morphology. So we're getting detail about these galaxies. And so you get things like, is there a spiral? Is there a bar? And so red spiral galaxies, that's the color they have for the whole galaxy, but they do have, they typically have more bars. So bars are doing something to galaxies, or the fact that if the galaxy turns red, it forms a bar. Those two things are related. The morphology and the galaxy-wide color are related. And so they also asked why the people were doing it. And the fun thing is that it's like, yeah, I'm actually excited to contribute to original scientific research. That's a big motivator for people to go and help. You do have to have this working the first time round. You cannot have a website that's not available. You cannot have a 404 error, because then people basically take up stakes and leave. But a lot of people loved discovering, loved helping, loved working in this online community. And so this has been such a hit that other projects have been launched using the Zooniverse. And so now we're looking for fish. Now we're looking for, we're counting animals in the Serengeti. There is handwriting projects. There are counting clouds in historical photographs. All this stuff is the kind of thing that people are good at doing and machines are not, or not yet, I would say. So things like Galaxy Zoo Hubble Edition happened. So Hubble has taken pictures of quite a number of galaxies. And so these things were turned into postage stamps and then classified. So the third data release happened. We're now edging towards the fourth data release. So you've got visual classification of anything observed by Hubble, lots of the Sloan Digital Sky Survey, but also DES, KIDS, Gamma, all these other surveys, their images have been classified by Galaxy Zoo. So if you already know a lot about your galaxies, but you want morphological classifications, then you can go to the Galaxy Zoo and see if they've already done it, probably. Even Illustris, which is a simulated galaxy simulation, produced fake galaxies, and they were sort of slid in while everything was being classified. So people don't like classifying fake things. I mean, if you say, here's a bunch of fake galaxies, and people don't want to classify them. So they just sort of slip them into the normal Galaxy Zoo process. And so you would just keep classifying. The good news is that means that's a kind of like a double-blind test. And so the illustrious galaxies can be used to calibrate whatever was classified by Galaxy Zoo. And there's lots of detailed questions about subsets of galaxies. So anything from like spiral structure to number of little star-forming regions, all those things have been done using Galaxy Zoo because it's such a large number of people, small investment individually, but everybody contributes. And then so this happens very, very quickly. So the Galaxy Zoo data is available. There are just the classification fractions are available as full catalogs for Galaxy Zoo 1 and 2, and for Hubble, and for CANDLES, and very soon also for DES. And so these are things that you can just download, and it has like a SDSS position, number, and then also all the classifications that they asked, all the fractions for the questions that they that are in this Galaxy Zoo questionnaire. But that's only half the interesting science that came out of it, or at least that was the main thing. That was the thing that we expected to come out of this stuff. But the calibration might be a little tricky, but the voting tally is really much better than anything else. The other benefit is that you get serendipity. You get serendipitous discovery of weird objects. And so with so many people looking at it and so many people going like, huh, what's that? You get very, very rare objects. And so Hanny's voorwerp is the typical example of that. That is on the left, you see what the Galaxy Zoo volunteers saw, which is basically, you would look at that blue thing and say, well, the detector, coughed or something, or that's just a stray light from somebody's flashlight or something. You just don't expect that to be a real thing on the sky. Especially, this is an RGB color image, so it's red, green, and blue. It's just in the blue. When does that happen, right? So when do you actually look at a picture and it just gives light off in the blue? Well, it turns out if that's an oxygen 3 cloud or oxygen 6 cloud, I think, it's an ionized oxygen cloud. Just that. And it turns out, yeah, that was a big cloud of gas that had just been ionized by this supermassive black hole in the galaxy up at the top. But it started with Hanny, who is a elementary school teacher and a big fan of Brian May. So she was classifying things, and she was just put in the the chat channel for Galaxy Zoo. Hey, I've seen this really weird blue thing. Can anybody tell me what it is? And the professional astronomers that were part of Galaxy Zoo always kind of answered these questions because it got everybody engaged. And they went, that's not an artifact, that's actually real. And so they followed it up with Hubble, and it is that ionized gas cloud. So she just called it the Dutch voorwerp. Voorwerp just means thing or object. And so it's Hanny's object. If you've ever noticed Native American names, for example, in the United States, or for example, the River Avon in England, Avon just means river in Old Saxon. But when the Romans show up, they went like, what's that? And they went, the river. And so it's the River Avon now, it's the river. And so we have voorwerps, we have objects. So that tickles me to no end. But you can get really rare objects that way, really strange, because people just noticed it and just flagged them as such. So not just did you get the classifications, you also get like a big pile of the absolute rarest things that you can look at. So things like this question mark galaxy, or all these really strange interactive galaxies, for example, like people made a note of it in the channel, in the chat room, and as a result, you end up with those weird, with the strange, with the unique. And so you can answer a question about galaxy morphology, or you can find really rare and serendipitous objects. And the third thing is that you now have training sets for future galaxy morphology machine learning. So artificial intelligence can go classify this, and it can do as well as crowds of people. So that's the whole point. Like, you now have a label set for your feature set. Okay, so I'll talk about that more in the last lecture. And so, for example, here's a project that I did, which was that here's an edge-on galaxy, and I'm, part of the edge-on galaxy classical look is that there's that dust lane in the center. There's a big dark lane in the middle. Okay, well, can I get the Galaxy Zoo to answer this question? This was not something that the Galaxy Zoo was designed for, but again, you can say, can I answer that with the questionnaire that I have? And so, is it an edge-on? Yes, and if that's so, is there anything odd? Yes, there is a dust lane. So basically, I can, if I use those two questions, then I can hopefully see if edge-on galaxy always have a dust lane. And so we don't rely on the single expert. And so this was predicted by Julian Del Canton in 2004, where she said, look, I'm looking at massive galaxies. They seem to have that color gradient. They seem to have dust lanes. And if I'm looking at smaller galaxies, they don't seem to have dust lanes. And the neat thing is like, this is a single expert making a prediction. You can then go and take that to the Galaxy Zoo. And so that's what we did. And it does not depend on the dust mass or the relative dust mass, but it does depend on the total stellar mass. So basically, yes, bigger galaxies have a higher fraction, slightly higher fraction of dust lanes, and then their lower mass brethren. So totally in agreement. Or, for example, this is a project that Bill Keel and I have been working on, you can look for overlapping galaxies. So again, this is one of those things that wasn't the question earlier, but we just asked on the chat channel, and people just started pouring these things in with, it's like, oh yeah, no, there's two overlappers. Oh, there's overlappers. And now it's basically a question in the later iterations of the Galaxy Zoo. And so we had the original idea back in 1992 by Bill Keel. And every time we sort of did one or two pairs because that's how many we knew of. And the neat thing is that with Galaxy Zoo, if you have lots of people inspecting these things, then it's ideal for Galaxy Zoo. It's really hard for a machine learning algorithm to identify. These things are pretty rare. It's really hard to figure out if it's, if it's a spiral arm or a separate galaxy, yet human eyes are much better at this. And so we found several thousand of them and classified the paired morphology as well. So like we got spirals, we got a face-on with an elliptical behind it, perfect. Or we got edge-ons, or we got small ones, or we got two ellipticals. And so you can just look at the amount of transmission, at the amount of light that's left through by the background galaxy through the foreground galaxy. And you can see where there's light missing, basically arguing a rotation argument. And so you can find missing light in the foreground from the background galaxy. So the background galaxy light is missing. And so you can see where the foreground galaxy is absorbing or scattering that light away. So that is the StarSmog project. That is the starlight absorption reddening through the survey of multiple occulting galaxies. StarSmog is also what the dust is. And so we look for those with Hubble later, and to go look for the dusty structures there. So that's kind of like you get all these different morphologies and all these different combinations of galaxies. But the neat thing is you can see that the light is missing. Especially this one is perfect. It's got a nice big elliptical in the back, and you can see the spiral structure being absorbed. And so who has the time? Like, where do all these people come from? So about the equivalent at the time was that when Galaxy Zoo 1 came out, also the app Angry Birds became really popular. And this is now a classic game or something like that. 200,000 man years or people years have been spent on Angry Birds. That's 300 million minutes a day. And so if you have 180,000 volunteers for Galaxy Zoo, they don't even have to spend as much as people typically do on a fun gaming app. So version, whatever you want to call it, the Galaxy Zoo crowd keeps classifying. More and more survey data becomes available. So it is with changing science questions. So this is kind of an indication of how that goes. These are all visual representations of the flow diagrams of the different questions that different iterations of the Galaxy Zoo did. So some of them answered more about the spiral structure, for example. Some of them were a little more interested in how clumpy things were, and other things were more interested if this were true or not, right? So the questions have evolved over time. But it's interesting to see that we can now answer all these classical morphological questions like how many galaxies are barred and how many galaxies have a ring or something like that, or is there a difference with color, and all these little morphological features we can actually link to global galaxy properties like color, star formation rate, stellar mass. All those things can now be interlinked because we have quantitative information on it rather than the qualitative ones we had based on our what the astronomers, the classical astronomers said. Okay, I'm going to keep going. See this? All right. Cool. So the last project that I wanted to talk about is that you can look for galaxy within a galaxy. You can look for star clusters. So this is the one of the later Galaxy Zoo projects. There's Galaxy Zoo projects or Zooniverse projects on, for instance, the Moon and Mars to look for geological features. There are lots of different science to turn images into quantifiable information using people to assess them. And this is another example of that, which is the Andromeda Galaxy that has been entirely imaged by the Hubble Space Telescope for about, sorry, I say entirely, a third of it has been imaged in several colors. So we have this gorgeous stretch of Hubble images. These are not individual tiles. Each individual tile is 16 Hubble pictures. So you see this kind of jaggedy, this is 667 Hubble pictures stitched together. So it is a huge Hubble, this is still the largest, highest resolution image of the night sky in existence. It is amazing. It has this wealth of information on this one galaxy. And what we're looking for is those little blue blobs, concentrations of stars. Now that again is incredibly hard for a machine learning algorithm to identify as a cluster of stars. So the Hubble imaging is here. This kind of gives you an idea of how many different pictures were taken in order to take the whole thing. It's called the Panchromatic Hubble Andromeda Treasury, the FAT survey. And so the idea was you'd mark, we had a circle drawing tool already for the Moon Zoo. So that drew around like, hey, there's a crater here and a crater here. And so we already had the tool. So the software infrastructure was there. And so the only thing we needed to do is mark things that were background galaxies seen all the way through Andromeda and clusters of stars. And so this is an animation of how fast that went. Basically, if you have many, many people draw circles for you, and you can weigh users, and you can weigh, you can do an average weighting for each circle, and basically say, oh, there's a cluster, it's this big, this is the typical radius, that's another grouping of stars, that's another grouping of stars. It took 8 months to set up and to verify that all our infrastructure worked, and a couple of people classified some of them, and then it was. I think it launched in the 1st of November, and we were done by Christmas. So thousands of star clusters classified, identified, and verified, and also 2,700 background galaxies seen all the way through Andromeda. So you can do something with those. So for citizen science, for this kind of thing, the rule of thumb is if you got hundreds of objects, just go do it yourself. Got thousands, do it yourself, and like with 2 friends. Got more than 10,000 objects, that's when it gets interesting to turn this into a Galaxy Zoo project. 90% of your effort is preparation. So this all has to work the first time round. Either it works smoothly, everybody can participate, there's enthusiasm, you answer the questions, you answer queries on the I guess Slack channel, or the channel that you've got going, and so it has to be fun. But that either works, or if you get a 404 date error, basically your volunteers walk out and never come back. It's fun and different, but it's still data. and it needs calibration and careful analysis. And that's a thing that's often skipped over. It's like, well, I got the voting tally, so I'm done. And it's like, no, that's when we get started. It's the future, or at least it's part of the future. So this is a basis, for example, how we train machine learning. Another part is that we can actually train a machine learning algorithm as the voting happens, for example. So it's basically becomes machine-assisted citizen science. I'll talk about that in the last class. So citizen science is a fantastic way to classify morphologies, to turn a large number of images that we have into morphological statistics, into morphological information. There's a rich data set. Nobody has even remotely published all the information there. So you can come up with your own answer, your own questions, and maybe you can answer it with a combination of questions that have been asked for the Galaxy Zoo project. It's very easy to set up a new and interesting Galaxy Zoo project. It's actually remarkably straightforward to load up all your images, set up a question tree. That part is easy. It actually comes down to, are you going to regret the questions that you put in? And then there's many other science applications of these universe. So many other science disciplines that are now using citizen science as well. NASA actively encourages citizen science components to their new astronomy programs. So if you have a new astronomy program and you have like, oh, this is how I could engage everybody, they actually encourage that and have funding for that. It's great for labeling for machine learning applications. Machine learning essentially needs training sets to say, this is, you can go out and get new data. It's like, this is the labels. This is a spiral galaxy. This is an elliptical galaxy. That's a barred galaxy. And so if you train something, it has to get to those labels. So for example, the Galaxy Zoo has been a Kaggle challenge. If you know what Kaggle is essentially pre-curated data sets with labels that you can learn, or you can say, okay, I've trained my neural network, or I've got this new clever idea to do another kind of machine learning. Look how well it does. And this is our calibration set, like the Galaxy Zoo 1, including the labels, have been machine learned over and over again. And part of the reason for that is that nobody minds if all the Galaxy Zoo data is out on the street, because there is no personal information there at all, and there's no issue with it floating around other countries or similar. The unexpected benefit, of course, is the serendipitous discovery of completely new objects, of things that either live for such a short time that there's only one on the night sky, or things that are so rare to happen that there's only one of them, or simply we hadn't noticed them before. And so the fact that you have a fresh view of citizen science on this particular thing, on this particular survey, makes it incredibly useful for serendipitous discovery. I cannot overstate how much luck typically plays a role in observational astronomy. So it's the kind of thing where if you see something like, oh, that's weird, that's usually when something interesting happens. And now you have many people going, oh, that's weird at the same time. So it really did come with a couple of really interesting new results. All right, I'll take questions real quick because my computer is acting up. So anybody? Nope. Okay, so I have one example of you may come to regret your questions later. So all these questions were workshopped beforehand. So we have to be very, very clear about all of this, right? So things like, is the galaxy simply smooth and rounded with no sign of a disk? So smooth or features. And so it doesn't say disk galaxy exclusively, because later on there are options that it's not a disk galaxy, but say an interaction, for example. And so you don't want to design that stuff out. Each of these questions have been very carefully considered, except that you have to beware that there's a question that's called, is there anything odd? And odd is a value judgment. What's odd to me might not be odd to you. And if you even ask everybody, you sort of asked all of society, what do you consider odd? In galaxies, what do you consider odd? And so if people said, "No, it looks fine," and then just voted, "Yeah," it's like, anything odd? Nah, we're fine. On to the next galaxy. And so all that's sort of a gatekeeping question to what's left. Is the odd feature a ring or a lens? And so they've scrapped that question, because essentially you got a function of what all of society considers odd for a galaxy, and that's a value judgment. And so that became and as a result, you got much less votes for dust lane or merger or something like that, because, like, well, it's not odd for a galaxy to have a dust lane, especially not edge on. So it's like, oh, that's not odd. Okay, keep going. And so that's a question we came to regret later. But it's interesting to see how important phrasing here is, and how important it is to test this stuff with many people, not just the 3 people in your group. So you can see that later in the let's see, where are they? Here they are. You can see that a little bit in the later versions of this of these questionnaires. Like, the odd question disappeared, and there's also a little bit of a rearranging. Like for example, we're interested in mergers. Mergers seem to do morphologically a lot, so you can have merging, tidal debris, both, or neither. And so that gives us good information, and we're forcing you to answer that question for every galaxy, right? So we're getting very good statistics on merger rates from this new Galaxy Zoo version. And then there's the other stuff, including overlapping galaxies, which is my favorite. So now we're basically getting statistics on how many galaxies happen to be overlapping, which is something different than merging, because that's the other thing that happened. People just hit on one of them instead of 2 of those things might be happening. So this is still in development, and especially if you think about doing this, the good news is that you don't have to use the galaxy. You don't have to use everybody if you want to use classification like this. You can set up a Galaxy Zoo classification tree like this. You can upload all your 6,000 objects and then simply classify them yourself. Just keep it private, or keep it within a small team, and just use the team as the volunteers to keep classifying this. A lot of survey teams are doing this now when they want to get visual classifications, but want to get visual classifications from just within the team. And it's a small enough project to do that with just 6 or 7 people, for example. So yeah, that's Galaxy Zoo. That's the citizen science application in astronomy on morphology. So we've learned a lot of new things. For instance, there are star-forming ellipticals. There are red and dead spirals. So something must have killed them. And so it's teaching us something more about galaxies and how they evolve and how we think they've formed. And so now we have more information on the morphology, and we can link it to other properties that we've derived in other ways. All right, I'm going to wrap it up and put this online, and I'll talk to you all next week. Thanks for coming in. Next week, I'll just do it at 1 p.m. as usual. I'll send around the Zoom link, and thanks for tuning in. All right. Talk to you next week.